Imagine this. During a baseball game, a pop-up is hit to an outfielder that is 72 meters away from home plate. He watches the ball into his glove, makes a clean catch, rears up, and fires the ball home with an initial velocity of 33 meters per second to prevent the runner on third base from tagging up and scoring a run. How long does it take the ball to reach home plate? For a projectile in motion, the acceleration of that projectile is satisfied by the equation dv over dt is equal to k times v, where k is the coefficient of resistance with respect to that object.
In our situation, using a baseball, we found the coefficient of air resistance to be 0.3. And because air resistance opposes the motion of the baseball, it had to be a negative.
With this previously determined value of k for a baseball, we can rewrite the equation as dv over dt equals negative 0.3 times v.
So let's find out how fast this ball gets home. We've already stated what our differential equation looks like.
The next step is to use integration to determine an equation that will tell us the instantaneous velocity of the ball at any point along its path to home plate.
So, in order to do this, we need to use separation of variables. We divide by v and move v to the left side of the equation, and then we multiply by dt and get that to the right side. As Kyle said, we will use integration to take this acceleration function into one that defines velocity.
Keeping in mind the rules we learned previously this year, any variable to the power of -1 when integrated becomes the natural log of that variable.
Looking at the right side of our equation, we see negative 0.3 dt integrates to negative 0.3 multiplied by t. Oh, and don't forget your plus c.
In order to isolate the variable v, for lack of a better term, you gotta e both sides of the equation, because I don't really know what you call that, but e it.
And what do you get? V equals e to the power of negative 0.3t plus c. And those rhyme.
When you have plus c included as part of your exponent for e, we can use our rules of logarithms to break that exponent into two separate e's, in this case e to the power of negative 0.3t plus e to the power of c.
And for some unknown reason, that e to the c jumps out front of the equation, and we get v equals c times e to the power of negative 0.3t.
Remember that we were given the initial velocity of the ball, which was 33 meters per second.
And we can use that to solve for c. Just plug 33 in for v, plug 0 in for t. You're left with only one variable. Isolate that, and you got your c.
Isolating c tells us that it's equal to 33.
Using this information, we can now find an equation that gives us the instantaneous velocity of the baseball for any value of t.
That equation will be v equals 33 times e to the power of negative 0.3t. We're only halfway done though, because the purpose of this problem was to find out how long it takes the ball to travel from the outfielder all the way to home plate.
Now, let's look at what we know. We know that the fielder is 72 meters away from home plate. We also know that the velocity equation is equal to 33 times e to the power of negative 0.3t.
The next step is going to be to use integration of our velocity function because that tells us the total change in position for the scenario. Remember though, we already know that the ball is going to change position 72 meters. That's how far it is from the outfielder to home plate. What we don't know is how long it's going to take the ball to travel that distance. So our integrand is going to look like 72 is equal to the integral from 0 to x of 33 times e to the power of negative 0.3t dt, where x is the time it takes the ball to travel that distance.
And of course, we all know what to do when we're integrating in AP Calc. You gotta u it. So we get our u to be equal to negative 0.3t, and our du comes out to be negative 0.3 dt.
If we want to substitute u and du into the integral, we're going to need to divide the inside by negative 110 and multiply the outside by negative 110 to keep things equivalent. And the integral looks like 72 equals negative 110 times the integral of e to the u du.
We know that the integral of EU is equal to EU. So after we integrate, we replace u with its equivalent, negative 0.3t, and we look to evaluate between 0 and x.
Using the fundamental theorem of calculus, we can plug in our limits and rewrite the expression as 72 is equal to negative 110 times the difference between e to the power of negative 0.3x minus e to the power of negative 0.3 times 0.
Notice that the second e is raised to the power of 0. Because any constant raised to the power of 0 is equal to 1, e being a constant raised to the 0th power is equal to 1.
Next, we distribute the negative 110 to each part within the parentheses.
Then we take away 110 from each side to get negative 38 on the left side. Then we divide both sides of the equation by negative 110.
That really big decimal there is now equal to e to the power of negative 0.3x.
Now we continue to isolate x by taking the natural log of each side. So now we find the natural log of that really big decimal to equal negative 0.3x.
Finally, by dividing both sides by negative 0.3, we determine that the time it takes the ball to travel from the outfielder to home plate is 3.543 seconds. While the throw from the outfield represents one application of calculus in baseball, there are many other ways that it's included in the sport. Let's take a look at another. The ball is hit towards the shortstop at 15 meters per second. The runner takes off towards first base at 7 meters per second. The angle created between the runner, home plate, and the ball is 65 degrees. What is the rate of change of the distance between the runner and the ball when the runner is 9.14 meters down the first base line?
Recognize that this situation creates a triangle between the ball, the home plate, and the runner.
Based on the information we were given in the problem, we can label the triangle with what we already know.
We know that side B is equal to 9.14 meters. We know that angle ACB is equal to 65 degrees. We know that dA over dt is equal to 15 meters per second, and dB over dt is equal to 7 meters per second. We still do not know the values of side A or side C, and we need those to find the change in C over the change in time.
To solve this related rates problem, we will use the law of cosines as a basis for determining unknown values.
But first, we need to find out how long it takes the runner to go 9.14 meters down the first base line.
By dividing 9.14 by 7, we find that it will take him 1.31 seconds to reach this distance.
Remembering that the ball is traveling away from home plate at 15 meters per second, we can determine that after 1.31 seconds, the ball is 19.65 meters away from home plate.
Now we know enough about the triangle to use the law of cosines to determine a value for side C.
By plugging in numerical values for each variable, and then simplifying, we can determine that C is equal to 17.83 meters.
In order to solve for dc over dt, we're going to need to take the derivative of our law of cosine equation. The derivative of the law of cosine equation looks like this.
Once again, we substitute in what we know and simplify.
Then, by isolating dc over dt on the left side of the equation, we can determine that it's equal to 13.61 meters per second.
Although calculus can be used to find the change in C over time, let's look further into the situation and see if our exemplary shortstop will make the play. A ball is hit at 15 meters per second towards the shortstop, who is playing 30 meters away from home plate. He fields the ball, which takes him 1 second, and throws the ball at 33 meters per second to the first baseman. All the while, the runner runs to the first base at a speed of 7 meters per second. If the angle between the runner, home plate, and the shortstop is 65 degrees, will the shortstop be able to make the play in time and get the out? Using our knowledge of rates, distance, and trigonometry, we can actually calculate if the play will be made. Now we look at the triangle created by the ball, home plate, and first base.
Similar to our last problem, dA over dt is equal to 15 meters per second, and angle ACB is equal to 65 degrees.
Let's take a look at this triangle. In order to solve this problem, we need to find the value of C, knowing that A is equal to 30 meters and B is equal to 27.5 meters. A being the distance from the shortstop to home plate, and B being the distance from home plate to first base.
Initially, it'll help us to know how long it takes the ball to reach the shortstop 30 meters away from home plate. To do this, we take 30 meters and divide it by 15 meters per second, which tells us it'll take 2 seconds for this to occur. Keeping the 1 second it takes him to field the ball in the back of our minds, we now move on to determine how long it takes him to complete the throw to first base.
In order to find this, we must know the value of c, which is the distance between the shortstop and first base. To do this, once again we use the law of cosines. Through substitution and simplifying, we find the distance between the shortstop and first base to be 30.97 meters.
By recalling that the fielder throws the ball to first base at 33 meters per second, we can take this distance, 30.97 meters, and divide it by the velocity of 33 meters per second to show that it'll take 0.94 seconds for the ball to reach first base.
By summing the 2 seconds it takes the ball to reach the fielder, the 1 second it takes him to field the ball, and the 0.94 seconds it takes him to get the ball to first, we can find that it takes 3.94 seconds for the fielder to make the play.
Now we need to compare this time to that of the runner sprinting to first base.
With the runner sprinting the 27.5 meters to first base at a rate of 7 meters per second, we can find that it takes him 3.86 seconds to reach first base.
By comparing the two times, it becomes evident that the runner will reach first base faster than the throw and should be called safe.
Therefore, the fielder will not make the play in time to get the out.
Too far.
Are we all good?
Oh, here comes my mom.
Only broken 3 windows. Ready?
Yeah.
Okay.
Oh,
Get past you. He
about.
goes too. There's no one coming third.
Get home!
God, this is fun.